Quantum entanglement stretches the meaning of the word to a concept that is difficult to comprehend. It can occur when two particles undergo superposition with each other. One example being the cooling of particles that are placed sufficiently close to each other, causing the overlapping of their quantum states. That is, the 4 quantum numbers that were discussed in the previous video. This is known as quantum superposition, caused when the wave properties of particles such as electrons and photons overlap. This event interlinks these particles, causing their fates to become intertwined. But does the overlapping of the quantum states of two fermions, such as electrons, clash with the Pauli exclusion principle? No. In fact, it is the very conservation of the exclusion principle that helps to explain the amazing features of quantum entanglement. It is because two particles cannot be in the same quantum state that a change in one will result in a compensatory change in the other entangled particle, regardless of the distance separating the particles. Further examples of events producing entangled particles are nuclear decay, a subatomic event that may cause production of a lepton and antilepton, which would represent an example of entangled particles. These events have enabled investigations into how gluons, which are the exchange particles of the strong nuclear force, contribute to the structure of nucleons. A more simple explanation of this process would be in regards to throwing two entangled coins. If one coin lands on head, then the other coin has definitely landed on tails. This happens even if one coin is on Earth and the other is on Mars. That's the essence of entanglement. Of course, the two coins must have undergone a process where their quantum states had overlapped and been superposed, making them indistinguishable from each other. Einstein coined a fitting description for this phenomenon. It's a spooky action at a distance. Quantum entanglement challenges our classical understanding of the universe, as it suggests a deeper connection between things than we previously imagined. A connection which transcends space and time. This is what makes quantum entanglement a fundamental principle of quantum mechanics. It underpins many aspects of quantum mechanics, such as the interdependence of quantum states. And it is not just a theoretical curiosity, but has actual real-world applications. These include quantum cryptography, photocatalysts, energy storage, and tissue engineering. It is the key to unlocking powerful new technologies. Technologies that could revolutionize computing, communication, and more. But first, let's look at the history of our discovery of this phenomenon. The story of the discovery of quantum entanglement can be traced back to the Einstein, Podolsky, and Rosen paper. Published in 1935, it was in response to Niels Bohr's idea that subatomic particles are governed by chance in the Copenhagen theory. Einstein described entanglement as a spooky action at a distance, because the spontaneous change in the second particle, no matter how far away it is from the first particle, appears to imply a transfer of information at speeds in excess of the speed of light. It was Erwin Schrödinger who termed it as quantum entanglement after reading the EPR paper. This after having devised his cat-in-a-box thought experiment to highlight deficiencies in the Copenhagen theory. The actual scientific evidence proving entanglement of particles was achieved by Clauser and Friedmann in 1972, a confirmation that has been repeated many times since, but without a clear understanding or explanation of the process by which it occurs. Nevertheless, entanglement is an accepted and real event. So let's study this role in greater detail. Entanglement is central to quantum mechanics. It plays a crucial role in several key concepts. 1. Being superposition. As mentioned at the start of the video, particles become entangled after existing in a joint superposition, causing the correlation of their properties. Another key concept is quantum measurement. Measuring one entangled particle affects the other instantly, even when they are millions of miles apart. This is a non-local correlation and departure from classical physics. It is a hallmark of entanglement. Quantum information science relies heavily on entanglement. It's essential for quantum computing, communication, and cryptography. Entangled qubits, the basic unit of information in quantum computing, can form a single system. Therefore, the state of one qubit can be determined by measuring the state of another qubit, which may be many kilometers away. This opens up new possibilities for computation. Entanglement allows for secure communication. This is known as quantum key distribution, or QKD. It ensures cryptographic keys are safe from eavesdropping, since the very act of observing the key changes it, alerting the communicating parties to any intrusion. It is clear that quantum entanglement holds immense promise and can lead to technological breakthroughs such as in quantum computing via entangled qubits. As mentioned in previous videos, these qubits increase the processing power of quantum computers to many times greater than current computers. This could revolutionize fields like drug discovery and material science. Quantum communication, as mentioned, is another promising area enabling secure communications. This is achieved through quantum key distribution, or QKD. It guarantees secure transmission of information. This is vital in an increasingly interconnected world. It protects against eavesdropping and cyber attacks. Quantum sensing and metrology are other fields that could also benefit, since entangled particles can create highly sensitive sensors. These sensors could be used in medical imaging, navigation, and environmental monitoring. They could detect minute changes in the environment, allowing for more precise measurements. Quantum materials is a burgeoning field including construction of superconductors, complex magnets, or topological materials. Researchers are exploring the use of entanglement to design new materials with exotic properties. For example, high-temperature superconductors could revolutionize energy transmission and lead to more efficient electronics. The future of technology is intertwined with entanglement, a powerful resource that has very real transformative possibilities. We will return to quantum entanglement in future videos. However, if you liked this video, please hit the like button, subscribe to this channel, and press the notification bell to be alerted to the publishing of new videos. We hope we are assisting you to stay curious.